Hello students. So we can start the fourth module of engineering chemistry. What we'll be discussing is stereochemistry. Now let us look at the syllabus of stereochemistry. So we start with isomerism, the study of isomers. Isomers means compounds which have same molecular formula but different structure and different properties. So we will classify isomerism, and in that classification you will be learning about structural isomerism. Structural isomers can be further classified into chain, position, functional, tautomers and metamerism. So we'll be discussing about that, and then we'll be seeing how we can represent three-dimensional structures of organic compounds on paper. So there are four methods to represent three-dimensional structures, namely Newman, Sawhorse, wedge and Fisher projections. So we will take substituted methane and substituted ethane as an example, and we can see how we can draw these structures. Then you have stereoisomerism, where we will be discussing about geometrical isomerism first. And in geometrical isomerism, we will be seeing the EZ system of naming. How geometrical isomers can be named using the EZ system. And then we move on to optical isomers, where we will be learning about chirality, enantiomers and diastereomers. Now enantiomers and diastereomers are different types of optical isomers. And then we'll be looking about the R and S notation, R and S system of naming optical isomers. That is similar to the EZ system. Finally, we'll be seeing about conformational analysis using ethane, butane and cyclohexane as examples. And towards the end, we'll be discussing about methyl substituted cyclohexanes. So this is the syllabus for stereochemistry. Now before we start, let us first go into dimensional structures of organic compounds, because once you familiarize with this, it will be easy for our future discussions. How can we represent three-dimensional structures of organic compounds on two-dimensional paper? So there are four methods. I've told that earlier. There are four methods. These four methods are very commonly used: wedge projection, Fisher projection, Sawhorse projection and Newman projection. Now out of these, the Fisher projection and the Newman projection are very commonly used. So that we'll study in detail. The Sawhorse and the wedge, they are used very less, but still we can see what are the different features of these. So let us start with substituted methane. Now before going, what is substituted methane? So this is methane, CH4. I have labeled the carbon as red just to distinguish it between the other groups. Suppose you change all these hydrogens and you put four different groups, then we get substituted methane. Example C, A, B, P, Q. A, B, P, Q can be any other functional group. Now in this case, you consider a general case of substituted methane. How can we represent the three-dimensional structure of substituted methane? You know that carbon is sp3 hybridized, so this will be tetrahedral in nature. So the best method is to represent the tetrahedral structure like this. Now this is called the wedge projection formula. You have to be careful, you have to just understand this thing. So this is the central carbon and you have these four groups. Now these straight lines, they represent the groups in the plane of this slide. Okay, in the plane of this slide. And the triangular line, that represents the projection towards us, and this dashed line represents the projection towards the behind, towards the back of this screen. Okay, So this is the three-dimensional structure. These two groups are in the plane of the screen. The group Q is projected towards the back of the plane and the group A is projected towards the front of the plane. So this is the wedge projection. Now if you take this wedge projection and if you compress it on a wall, suppose you just press it from here, okay, from this direction, if you are pressing it, you will get a planar structure, and that structure will look something like this, and this is called the Fisher projection. So just press this on a wall. So the group Q, it will come down. This group A, it will go up, it will flatten, and you get a structure like this. So A, B, P and Q. So this is the Fisher projection. So Fisher projection is a planar representation of wedge projection. Now let us move on to substituted ethane. In substituted ethane, the other two projections, that is Sawhorse and Newman, they become important in case of substituted ethane. They cannot be drawn in case of substituted methanes. So in substituted ethane, this is ethane, CH3, CH3. I have labeled one carbon as red and the other carbon as blue. The red carbon represents the front carbon and the blue one represents the back carbon. So suppose you are viewing from a direction like this, from this side, then this is the front carbon and this is the back carbon of ethane. Now if you remove all these hydrogens and replace it with bulky groups or other functional groups, we will get something like this. This is substituted ethane. So you are going to view this molecule from this direction. So this one becomes the front carbon. So A, B and C are attached to the front carbon. P, Q and R are attached to the back carbon. Now substituted ethanes are of two types. One is called the eclipsed form and the other is called the staggered form. What is eclipsed and what is the staggered form? The eclipsed form, the groups on the front carbon and the back carbon are eclipsed. Okay, eclipsed means you know what is eclipsing, one coming in front of the other. So these are eclipsed, and so these groups are very close to each other, or they are the closest to each other in this structure. Whereas in the staggered form, the groups on the front carbon and back carbon are away from each other. So all the groups are maximum away from each other. That is the difference. Now when you see the structures, you can understand. So in the eclipsed form, the groups are eclipsed and so they are very close or the closest to each other. And in the staggered form, the groups are away from each other, maximum away from each other. So this is the Sawhorse projection for eclipsed substituted ethane. Now you can see this is the front carbon, okay, and this is the back carbon. So these groups A and P, they come one before the other. P comes behind A. If you are viewing from this side, then P comes behind A, or this is eclipsed. B and Q, they are eclipsed. C and R, they are eclipsed. So this is the Sawhorse projection formula or Sawhorse projection for substituted ethane eclipsed. Now the same Sawhorse, you can convert it into another form which is a little more easier or a little more, it is more used, and that is the Newman projection. So this is the Newman projection of eclipse. See here, this is the front carbon, okay, and the back carbon, that is represented by this circle. So this represents the front carbon and this circle represents the back carbon. So you can see here these two groups A and P, they are eclipsed. Actually this P should be behind A. So just for a view, I have drawn it a little bit on the side. A and P are eclipsed, B and Q are eclipsed, C and R are eclipsed. So this is the Newman projection for eclipsed substituted ethane. The same Newman, now these two are three-dimensional, Newman and Sawhorse are three-dimensional. We can convert this into a two-dimensional picture. that is the Fisher projection. We have seen the Fisher projection earlier. So this is the Fisher projection for eclipsed substituted ethane, and here you can see this is the front carbon and this is the back carbon. So these groups A and P, they are at the terminal positions, and you have B, C, Q, R on the two sides, left and right. Now together, so this is the Newman and this is the Fisher. If you view them together, you can understand how to draw this. So you can see here, this is the front carbon and this is the back carbon in the Newman. So in the front carbon you have A projecting upwards, and so here also A in the front carbon, A is projecting upwards, and the back carbon P is projecting upwards. So you, in the Fisher, the P will be projecting downwards. The back carbon projects downwards and the front carbon projects upwards, these two groups. Okay, then left of A you have B, so you write that left of A is B, right of A is C, so you write that here. Similarly, left of P is Q, so put that on the left, and right of P is R, so put that on the right. So this is how you can convert a Newman projection to the Fisher projection. Newman and Fisher, these are most commonly used in stereochemistry. Now instead of drawing like this, we can draw the Newman in another way. These groups A and P can be projected downward also like this. Okay, the same thing. You just rotate the earlier figure, you will get this one. So it's the same thing. A and P are projected downwards. Then you have B to the right, C to the left, and you have R to the left, Q to the right. So how will you represent this in the Fisher projection? This is the Newman projection for eclipsed, and the Fisher projection. So these are the front and the back carbons like earlier. The Fisher projection, it will be represented like this. So you have the front carbon at the lower part and the back carbon at the upper part. So that is there is a small difference from the earlier case. In the earlier case, the front carbon was above the top portion, but now the front carbon is in the bottom portion. Let us compare better. So you have the A group, that front carbon A is projecting downwards, and so here also the front carbon is written down and A is projecting downward. P, that is a back carbon, that is written upward, that will be projecting upwards. So this is how A and P, these are opposite. Okay, then to the left of A we have C, that is written here. To the right of A we have B, that is written here. Again P, to the left you have R, and to the right you have Q. So that you write as it is. Only thing is, these groups which are projecting upwards or downwards, that has to be written in the vertical line. The other groups, they are written in the horizontal line. So you see here, when the front carbon is projecting downward, in the Fisher also it is written at the lower part, and if this is projecting upward, it is written in the top portion. That is the only difference. So these are the Newman and Fisher projections for substituted ethane eclipsed form. Now coming to substituted ethane staggered form, this is how you represent a staggered conformation. You can see here these groups A, B, C, they are written like this. P, Q, R is rotated. Okay, earlier the P was projecting upward just like this itself, but now it is different, it is projecting downward. So what is the point here? The distance between these groups are at the maximum. A and P, they are at maximum distance. B and R, they are at maximum distance. C and Q, they are at maximum distance. So all the groups are at maximum distance. Little bit you can understand more if you look at the Newman projection. This is the Newman projection for staggered substituted ethane. So you see here A and P, they are exactly opposite to each other, maximum distance from each other. B and Q, they are maximum distance. R and C, they are at maximum distance. So this is a state of minimum potential energy, and the staggered form normally will be more stable than the eclipsed form. Fisher projection is possible only for eclipsed form. You cannot draw the Fisher projection for staggered form. So in staggered form, you have only Newman projection and Sawhorse projection. Whereas in the eclipsed form, you can draw Newman, Sawhorse and Fisher projections. Out of them, Fisher and Newman, they are more